So we will continue today chapter 16. Now we will introduce a new concept, which is relative motion analysis in case of points in space. Okay. So here we have already introduced relative motion in chapter 12. But as you remember, what was the condition? We said that if we have 2 points A and B, we put a frame on A or B, okay, that is translating with the points, and therefore if you want to get the relative velocity of B with respect to A, then we can say that the relative velocity of B relative to A is VB minus VA, and AB relative to A is AB minus AA, with the condition that the frame at A is translating. Now, what we will do in this analysis here, we will consider a frame that is rotating, not translating, and this will be, the analysis will be very different in this case. So our purpose now is to relate the relative motion of 2 points, considering that for one body, we have a frame that is rotating. And we will see how the analysis will be different from the case where the plane is translating. So first, in order to be able to relate relative velocity and relative acceleration, we will go back to the definition. Okay. So first, you start always from the relation of position. The position relation is RB vector equals to RA vector plus RB relative to A vector. And now, when we derive this relation as a first time with respect to time, we get a relation between velocities. And when we derive it again, we get a relation between accelerations. Okay? Now, just to start with, okay, we will do relative analysis in several cases. First, we will consider 2 points of one rigid body, okay, and then we will move to the case of any 2 points, general points. They can be on different bodies, okay. So when we will do the general analysis, we will take a frame that is rotating with the point. Now here, in this analysis, in this section, we will just still consider a translating frame. So if you remember, last time when we introduced the relative velocity concept, let us go back to the figure. So if you remember, when we did the analysis of general motion, we decomposed general motion into translation of point A plus rotation of B around A. So keep in mind that you have to approach when you do relative motion. In case you have a translating frame at A, you will have a certain equation. And in case you have a rotation frame, a rotating frame at A, the equation will be different. Okay? Last time we introduced the first approach that considered 2 points of one rigid body. And in this case, we take at A a frame that is translating, not rotating. In case the frame is translating, then when you look at B relative to A, B is doing just rotation about A. Okay? While if you take the frame rotating with the same angular velocity of the rod, then you will see that B is fixed relative to A. Okay? So in case of translating frame, the relative motion of B with respect to A will be just a rotation. And then we have related VB to VA as follows: VB equal VA plus VB relative to A, where VB relative to A represents the rotation of B with respect to A. Now we will do the same approach for acceleration. We are still considering a translating frame, and in a further step, in next paragraph, we will see what is the effect of a rotating frame, of taking a rotating frame. And we will see together in which cases, in which problems we will use the formulas of translating frame, and in which problems you will use the formula of rotating frame. So as a first rule, whenever I have one rigid body and 2 points of the same body, okay, so you don't have relative motion between the 2 points, the distance between the 2 points is fixed, okay, then you will use a translating frame. However, if you have, for example, a person on a body and this person is able to move on the body, then we will use the concept of rotating frame. We will see why. Because in this case, this point will be able to move on the body, will have a freedom of motion. However, when you take 2 points of the same body, the distance between them cannot change. So the relative motion of B with respect to A, if I take a translating frame, will only be rotation. It cannot be anything else. Okay? So in general, this rule of translating frame, which decomposes the motion into rotation plus translation, is considered for 2 points of the same rigid body. Okay? So we have seen last time how to relate velocities. Now we will see how to relate accelerations in this case. So the concept is the same. Okay? Because the 2 points are on the same body, when I take a translating frame at A, B is doing rotation with respect to A. So if I think about decomposing the acceleration vector, then I will obtain the following. The acceleration of B is equal to the acceleration of A plus the relative acceleration of B with respect to A. And the relative acceleration of B with respect to A is decomposed into tangential component and normal component. Because you know that in rotation, when you have rotation, the acceleration can be decomposed into tangential and normal. So ABAA will represent the absolute accelerations of B and A, and these two components, tangential and normal components, represent the acceleration due to rotation of B about A. And for the vectorial expression, we have seen last time that the tangential acceleration AT can be written as alpha vectorial or B relative to A. So this is the tangential acceleration of B relative to A. It can be written as a vectorial product of alpha and R. And concerning the normal acceleration, also we have seen last time that the normal acceleration vector can be given by minus omega square or B relative to A, because we are working in 2D here. So this is the normal acceleration. And in this way, if we have any 2 points on the same rigid body, we can use this approach to relate their accelerations. Okay? Now, let us do some practice on how to relate accelerations of 2 points on the same rigid body. The rod AB is confined to move along the inclined planes at A and B. If point A has an acceleration of 3 meters per second square and the velocity of 2 meters per second, both directed down the plane, at the instant the rod becomes horizontal, determine the angular acceleration of the rod at this instant. So here, what do we have? First, we have a rod. So it's one rigid body. And we know characteristics of 2 points. We know something about A and information about B. Concerning point A, we know everything about it. We know the direction, we know the sense, and we know the magnitudes of its velocity and acceleration. So for A, nothing is unknown. For B, what we can see from the figure is that B is moving on a straight line. So since A will move up, will move down, B will move up. So we can be sure that VB will be upward. And let us assume that AB is upward also. And from the sign, we can determine if AB is negative or positive. Now, the question is to determine the angular acceleration of the rod. So until now, we have two unknowns, VB, magnitude, AB magnitude, and also we have omega AB unknown and alpha AB unknown. So we have 4 unknowns. 4 unknowns requires 4 equations or 2 vectorial relations. We need 2 vectorial relations to be able to solve the system, because each vectorial relation will allow us to solve for 1 unknown. Okay? So if we look at our figure here, we will relate first, the first vectorial relation will be by relating velocity of B to velocity of A. This will give us 2 equations with 2 unknowns. When we write the relation of velocities, what will be the unknowns that we will calculate? We will calculate VB and we will calculate omega AB. And when we write the relation between acceleration of A and acceleration of B, the 2 unknowns we will calculate are magnitude of AB and alpha AB. In this way, we will be able to solve for our 4 unknowns. And why we choose to use the formula of translating frame? Because A and B are 2 points of one rigid body, and the distance between them is not changing. Okay? So relative to A, B is doing rotation when I consider a translating frame as A. So I can apply the formulas we have seen together. So the first formula to apply is the velocity relation. Okay? Now, if you remember, also for the velocity calculation, we have 2 approaches, or the vectorial one, or the instantaneous center method. I will do both for you here to see that both can be used in order to get information about the angular velocity. So let us start first with the vectorial method. If you want to apply the vectorial method here, we will write the following. We will write that VB vector is equal to VA vector plus omega AB vectorial AB. So this is our vectorial relation that will relate the velocities of points A and B. Now, in order to obtain our 2 equations, we should replace each vector by its expression. So I should decompose each vector into ij components. And of course, omega will be along k, because in 2D motion, omega is perpendicular to the plane of motion. So first, for VB has an angle of 45 with I. So I can write, instead of vector VB, I can write VB magnitude times cosine 45 I equals plus VB magnitude times sine 45 J. In this way, I decompose the vector into 2 components, in I and J, equals to. Now from the other side, I have first V of A. As you can see, for VA, it's downward, and the magnitude is 2 meters per second. So it's along X, it's positive. It's plus VA cosine 45 along I. But along J, it's a negative component. So minus VA times sine 45 along J. So this is the velocity vector, okay, VA. I can just replace directly VA by 2, so 2 cosine 45 I minus 2 sine 45 J. And concerning omega AB, I should do an assumption if it's clockwise or counterclockwise. If I assume it's counterclockwise, so it's along positive K, so it's plus omega ABK vectorial AB. And as you can see in the figure, the position of interest is the horizontal position. At this position, since AB is horizontal, it has only a component along I. So vectorial tan I. And now all I have to do is to develop my relation. So I have that K vectorial I is plus J. Okay, if you remember the circle, I, J, K, I. Ki positive. So I can replace this term by 10 omega AB J. And now I'm ready to compare along I and J. Okay, so I will start by comparison along I. What do I get? If I compare terms along I, so along I have the following. I have, from the first side, I have VB cosine 45 equals to, from the other side, I have along I 2 cosine 45, and that's it. Okay, I don't have any other component along I. So from this relation, from this comparison, I can say that, so VB equal to, okay, so V of B is equal to 2. I got my first unknown. Now, if I compare along J, the equation will be, from the left side, the component along J is VB sine 45. So I can directly replace VB now, okay, by its value. So 2 sine 45 equals to, from the other side, I have minus 2 sine 45 and plus 10 omega AB. So as you can see here, I can reduce the value of omega AB. So omega AB is equal to 4 sine 45 over 10. So 0.4 sine 45. And I got my two unknowns, VB and omega AB, using the vectorial method. Any question on the vectorial method? Okay. Now, we will do together another method to find VB and omega AB, but now using the concept of instantaneous center. Okay? So if we want to use another method, sometimes we will see here that it will be easy in this example, for instance. Because look, we know the direction of VA, and we know the direction of VB. And we said that in the method of instantaneous center, if we know the direction of two velocities, then it will be enough to locate the instantaneous center. Why? Because the instantaneous center should be on the perpendicular to VA, and also it should be on the perpendicular to VB. So this is a 90 degrees angle. Why it's 90 degrees? Because from geometry, this is 45 and this is 45. And since we know that the length of AB is 10, so this length is 10, then by simple geometry calculation, we can say that this length, the distance between A and the IC, is simply 10 cosine 45. Okay, so we can write that the distance between A and the IC from geometry is equal to the distance between B and the IC, and is equal to 10 cosine 45. Okay, so now we know the distance from A to the IC, and we know VA. So how we can calculate omega? We can simply say that omega is VA over the distance between A and the IC. So in this way, we just have to replace VA is equal to 2, and the distance is 10 cosine 45. So in this way, we can get omega again, the same value. You will get the same value for omega. And now, once we got the value of omega, we can say that we can find VB, because VB can be written as omega AB times the distance from B to the IC. And you can directly deduce, since the distance from A to the IC is equal to the distance from B to the IC, so VB will be equal to VA equals to 2. And then we obtained again the same result. But you can see here that in this problem, the instantaneous center method is easier because the geometry is simple. You can directly say that these two lengths are equal. So VA equals to VB. And to get omega, you do VA over this distance, and that's it. Okay? Any question on the instantaneous center method? So now we have obtained omega AB and VB in two methods. Now we will move to determine the angular acceleration of the rod. So always, even if they don't ask you for omega, you cannot calculate the angular acceleration without passing by omega before, because in the acceleration vectorial relation, you have omega. Okay? So let us see here what we should do. So first, we have that AB is equal to AA plus alpha vectorial AB minus omega square AB. This is the vectorial relation relating points A and B. Okay? So let us apply it, okay, as we did for the velocity. First, the acceleration vector of B, we have in the figure that A is moving down, B is moving up. Okay, so as we did for the velocity, AB can be decomposed into AB cosine 45I plus AB sine 45J. Now concerning point A, we know that it's 3 meters per second square downward. So it has positive component along I, negative component along J, like the velocity. So it's 3 cosine 45I minus 3 sine 45J plus alpha is the angular acceleration. It's along, we can assume that it's counterclockwise. And from the calculation, we will verify if it's positive or negative. So we put alpha k vectorial RB relative to A. RB relative to A, as we have seen in the velocity relation, is 10I minus omega square AB. So as you can see here, you need omega to find, to be able to calculate the other unknowns, because already your unknowns are AB and alpha. So in order to be able to use this relation and get your unknowns, you should before get omega. And this is what we did. We got omega or from the vectorial relation or from the instantaneous center method. So now, all we have to do after replacing omega is to do the expansion. So here you have alpha k vectorial 10I. K vectorial I will give you 10 alpha j. And now you are ready to do the comparison. Okay? So first we compare along I. What are the terms along I? Along I, from the left side, you have AB cosine 45 equals to, from the right side, you have 3 cosine 45 and minus 0.238 square times 10. So this is your first relation. In this relation, the only unknown is AB. So you can get the value of AB. Now we'll do the same for comparison along J. Along J, on the left side you have AB sine 45, and AB we have calculated it from the previous step, so we know it now, equals to, from the other side along J you have minus 3 sine 45 and plus 10 alpha. Okay, so please just here fix this. This is alpha bold letter, so it's a vector, or you replace it with alpha k. Okay, so now you have two equations with two unknowns, so you can get AB and you can get the value of alpha. And since you obtain positive results, this means that the direction you assume, the sense you assume for both is right. So AB is upward and alpha is counterclockwise. Any question on this problem? Okay, another problem. The spool unravels from the cord such that at the instant shown, it has an angular velocity of 3 radians per second and an angular acceleration of 4 radians per second squared. Determine the acceleration of point B. So we have alpha and omega, as you can see here. Okay, and in this case, we are interested in getting the acceleration of this point here. Knowing that we have rolling without slipping at A, about A. Okay, so here, as you can see, we know omega and alpha of the rigid body, and we want to determine what is the velocity of B and the acceleration of B. So here they just asked directly for the acceleration. What is the acceleration of? Whenever I have a rigid body, I will try to relate points. So I can relate B to A, or I can relate B to point G. So I should see what point I know information about. Do I know velocity and acceleration at A, or velocity and acceleration at G? So first, concerning point A, please pay attention for something. When we say rolling without slipping, okay, this means that at this point you have same velocity, but not same acceleration. So don't confuse this. So you can say that V of A is 0 because we have rolling without slipping, and this cord is attached to a fixity. So as the cord has, the points of the cord has 0 velocity. And since we have rolling without slipping, we can say that VA is 0. But we cannot say that AA is 0. Please pay attention. Because what is common is the velocity and the tangential acceleration, but not the normal one. Because the point of the cord has 0 acceleration. However, the point of the wheel, as a point of the wheel, A has a normal acceleration. So we cannot say that AA is 0. We can say that A tangential of A is 0, but not A normal. Okay? So since we don't know the value of A normal, then we don't know the acceleration of A. So A normal at A, we don't know it. So we should try to look at another point. There is a point on my wheel for which I can know the velocity and acceleration. Which point do you think? Which point I can find its acceleration easily? What do you think? Which point I can calculate its acceleration in this figure?
J.
Yes, very good, G. What will be the acceleration of G? Why for G it's simple? You know why? Because look at your
لأنه ما فيها شيئان.
Very good. لأنه الجي بعرف الموشن تبعه. اوكي بعرف انه it's moving along a straight line. بينما البوينت A اوكي it's different. اوكي يعني البوينت A عم بيتغير بكل لحظة، عم يجي حدا محله. so البوينت G هو الوحيد اللي قادر انا easily شوف الموشن تبعه. G is always parallel to the chord، يعني حيمشي على straight line. بما انه G عم يمشي على straight line يعني it has a rectilinear motion، يعني ال velocity تبعه وال acceleration are both along this line. Okay, and since I have rolling without slipping, whenever I have rolling without slipping, what can I write? Velocity of G equals to omega of the rigid body times the distance from G to the instantaneous center. The instantaneous center is A because VA is 0. So V of G is omega times AG as magnitude, okay? And it's directed downward because omega is clockwise. So as the chord will move clockwise, G will go down, okay? So VG is downward and it's equal to omega times AG. So AG here is 0.15. So at any instant, VG can be calculated as omega, since omega at this instant is given, okay? So we can replace it. So, but in general, at any location, VG is 0.15 times omega. And since it's a rectilinear motion, then G will just have a component, a tangential component, no normal component for G motion. So because it's a straight line, okay? So I can write that AG is simply the derivative of VG with respect to time. And the derivative of VG with respect to time is 0.15 times d omega by dt. So 0.15 alpha, because the derivative of omega is alpha. These two relations are valid at any point. In particular, at the instant shown, they gave us that omega is 3 and alpha is 4. So we know VG at this instant and we know AG at this instant. Okay? So, and concerning the direction, the sense, you can know it from the right-hand rule. So look, omega and alpha are clockwise. So both, in order to rotate about A clockwise, VG and AG should be down. Okay? So now we know that V of G vector is equal to minus 3 times 0.15J. So it's minus 0.45. While concerning acceleration of G is equal to minus 4 times 4 J. So it's equal to minus 16 J. Sorry, minus 4 times 0.15. Minus 4 times 0.15 J. So it's equal to minus 0.6 J. Okay? Now I am ready to apply the vectorial relation to get velocity of B. So to get velocity of B or acceleration of B, they want here the acceleration of B. To get the acceleration of B, all I have to do is to relate B to G. So I can say that acceleration of B is equal to acceleration of G plus, so let us put it here in vectors. So acceleration of B is equal to acceleration of G plus alpha of the disk, vectorial GB, minus omega square times GB. And now all we have to do is to replace each component by its expression. So for point B, I have that it's unknown. I want to get it. So I can decompose it into x and y components. Okay, so it's equal to acceleration of g is, I can replace by minus 0.6j. Concerning alpha, since it's clockwise, so it's minus 4k. So plus minus 4k vectorial GB. As you can see here, GB is an upward vertical vector. So GB is plus 0.225j minus omega square. Omega is given, so minus 9 times GB, and GB is again 0.225j. So now k vectorial j is minus I, and already we have a minus, so it's plus, and then we can get the acceleration vector simply. So you can see here that by applying the relation we did together, we can determine ABX and ABY. And now you can verify that point A has a normal acceleration. Okay? So if you want to calculate acceleration of A, you can relate it to point G. And you will see that the tangential acceleration of A is 0. You can verify this, while the normal component is not 0. So let us write it together. In order to calculate AA, we can just write that AA is equal to AG plus alpha vectorial GA and minus omega square GA. Let us replace, and you will see that the tangential component will be 0. So we have that AA is equal to, we will replace AG by its value. AG is minus 0.6j. Concerning alpha, it's minus 4k. And for vector GA, it's along minus I. So it's minus 4k vectorial minus 0.15i. And minus, we have minus omega square GA. And GA, we can directly replace GA by minus 0.15i. So now, if you do the expansion, you have minus minus, so it's plus. K vectorial I is plus j. So you have here, you will get minus 0.6j and plus 0.6j for the vectorial product. They will cancel out. So the j component will cancel out, and you will only be left. So as you can see, you verify that the tangential acceleration is 0, and you will get just omega square 0.15 omega square along I. So as you can see here, it's always a relative analysis. So here, when we find the acceleration of A, we are taking a frame, a translating frame at G, and looking what is the motion of A relative to G. A relative to G is doing rotation. Okay, so it has a normal component. And G also relative to A is doing rotation. Okay, but when we calculate the absolute value of acceleration of G always will be downward. So This is why G is doing a rectilinear motion. However, for A, it's different. Okay, A at this point, at each instant, a new point is replacing it, and therefore you have that the tangential component at this point at any instant is 0, while you have a normal component directed towards G. So at any instant, the point in contact with the chord will have an acceleration towards G, while G will always will have an acceleration that is along downward along G. Okay. Any question on this? So let us do another problem on this. The crankshaft AB of an engine turns with a clockwise angular acceleration of 20 radians per second square. Determine the acceleration of the piston at this instant as shown. At this instant, omega AB is equal to 10 radians per second, and omega BC is equal to 2.43 radians per second. First, هون أعطونا extra information. كان فيهم ما يعطونا omega BC. So هيدا الجيفن مش ضروري يعطونا إياها will tell you why. So they can just give you, if they just give you omega AB and alpha AB, you will be able to find omega BC and alpha BC. Okay? Why? Because if you look at your figure, what is happening? You have two rods, AB and BC, that are connected through pin B. So you have two rigid bodies. Okay? And you can relate the motion of A and B through vectorial relations, and you can relate the motion of B and C through vectorial relations. What are your unknowns? If they gave us alpha AB and omega AB only, what will be our unknown? We will have as unknown omega BC. We can assume, for example, it's counterclockwise. We have also alpha BC that is unknown. And of course, for point C, we just know that is moving along a slot, so it's doing rectilinear motion, point C, but we don't know the magnitude of BC, and we don't know the magnitude of AC. So we have 4 unknowns in this case. And if we have 4 unknowns, we need 4 equations. So as usual, we need vectorial relations. So you can relate velocity of C to velocity of B, and acceleration of C to acceleration of B. Then you will have 2 vectorial relations, which will give you 4 equations with 4 unknowns. Okay, so this is the strategy to calculate these unknowns. Now, concerning in this problem, they gave you omega BC to reduce the steps of solution. And if they give you omega BC, then no need to do the vectorial relation for velocity, because the purpose of writing the velocity vectorial relation is to get omega BC. But since omega BC here is given, they gave us the value of omega BC. So we need only to get the acceleration, okay? We need only to relate acceleration of C to acceleration of point B. First, to do this, we will write the vectorial relation between the 2 points. So we can write that AC is equal to AB plus alpha BC vectorial BC minus omega BC square times vector BC. Now I will replace each vector by its expression. Concerning point C, I just know that it's moving vertically. So this is ACJ. AC along J. Equals to for point B, okay, I can get the acceleration of By, because as you can see on the figure, B is doing rotation about a fixed axis. B is rotating about A. So since B has a rotation about fixed axis, we can say that AB is decomposed into two components, tangential component and normal component. Now, to get AB, you have two methods. You can do the vectorial relation to relate AA and AB if you want, or you can say, as we said, you decompose it into normal and tangential. Okay? You know that in the circular motion, the tangential component, this is AB tangential, will be equal to what? AB tangential is equal to alpha AB times the radius, okay, times the radius, which is AB, while AB normal is omega square AB times the radius. So omega square AB times the radius. Since we know the value of omega AB and we know the value of alpha AB, then AB normal and AB tangential are known. So just I have to decompose them into IJ. And as you can see in the figure, the angle between AB and the vertical is 45 degrees. Okay? So this means that AB tangential is doing 45 with the horizontal. And also AB normal is doing an angle of 45. So خلينا نظبطها شوي عجقة الفيجر. Okay? So this is the angle between AB tangential with the horizontal is 45, because here you have 90 degrees and this angle here is 45, so this is also 45. Okay, and AB normal is along BA, directed from B towards A, so also it's doing an angle of 45 degrees with the horizontal. Therefore we can write now that ACJ is equal to, for AB, first the tangential component, okay, is, as we said, alpha. The magnitude of it is alpha, which is AB, which is 20, times the radius, which is AB here, equals to 0.25. So 20 times 0.25, this is the magnitude. Now concerning the direction of AB tangential, it's doing 45 degrees with I and it's upward. So it's plus cosine 45I and plus sine 45J. This is AB tangential. So let me write it for you here. So this component is AB tangential, okay? Now we will write AB normal. So plus, for AB normal, as we said, the magnitude is omega square AB times R. This is omega AB, it's 10, and R is 0.25. So it's plus omega square AB, which is 10 square, times AB, which is 0.25. Now, for the direction of AN, it's from B towards A as UN. So it has a positive I, negative J component. So it's cosine 45I minus sine 45J. Minus sine 45J. And now, so we are done with AB. So this is AB normal. Okay, this is AB normal. We still have the other terms. So it's AB plus alpha BC. So we assume that alpha BC is counterclockwise. So plus alpha BCK vectorial BC. Now what is vector BC? if you look at this figure, BC vector, BC is doing an angle with the vertical of 13.6. So if I decompose BC, it has a positive I, positive J component. The component along I is BC sine 13.6. So it is 0.75 times sine 13.6 along I. And along J, it is plus 0.75 times cosine 13.6 along J. So this is vector BC. And now the last term will be minus omega square BC, which is given, it's 2.43, okay? So I can directly replace, so minus 2.43 square times vector BC. And vector BC هو اللي كتبناه هلا 0.75 sine 13.6i plus 0.75 cosine 13.6j. And now you have everything. All your terms are known. You just do the expansion to get the value of you. Yani you have two unknowns in this relation, AC and alpha BC. So you will do your expansion and compare along I and J. So you will obtain two equations with two unknowns. Let us see the details of the expansion together. So as we said, look, the first step, they find the vectors needed, okay? So since you need vector BC, you will decompose it into two components. So you need vector CB, and also you need vector AB, in case you want to use the vectorial method to get acceleration of T, okay? So here they got the vectors required for the calculation, the position vector AB and BC as a first step. Then for point B, you have two methods, as we said. أو نعمل A and AT, as we did together, or you can use the vectorial method, and you can simply say that I will relate B to A, okay? And since A is fixed, يعني نحن بدنا نحط plus AA, but since B is rotating about fixed point A, يعني A is fixed, so AA is 0. So you can get AB or by the method we did, or by doing alpha AB vectorial AB minus omega square AB times AB vector. So just you replace alpha AB. Since alpha AB is clockwise, so it's minus 20k. Position vector RB is vector AB that we got in the previous slide. So by just decomposing, as you can see here, vector AB has a negative projection along I. It's minus AB cosine 45, okay? And along J, it's plus 0.25 sine 45. So this is vector AB. You just replace it into equation. And concerning, so if we go back to the slide of calculation, so it's minus and minus omega square AB times vector AB. So here, when you do the expansion of these terms, since you know alpha AB, RB, and omega AB, you can get vector AB, so I and J component. So if you compare the two methods, you will get, of course, the same result, because this component will give you the tangential acceleration, and this one will give you the normal acceleration. Now, we move now to C after calculating AB. So to calculate AC, we will apply the relation now between B and C. So pay attention. When you apply between A and B, you use alpha AB and omega AB in the relation. Now, when you apply for rod BC, then you put alpha BC and omega BC. And now you replace. So AC is unknown in magnitude, so I put ACJ equals to, I replace AB by the value I got from the previous step. I assume that alpha CB is counterclockwise, so it will be alpha CBK. Vector CB is already calculated in the previous step, cosine 13.6 or sine 13.6. and minus omega square BC times vector BC. So as you can see here, it's a vectorial relation with two unknowns, AC and alpha BC. So now you do the expansion and you compare along I and J. If you want here, لأنه ما سألوكم عن AC, you can just compare to get alpha BC. Okay, and if you compare along I, you will get directly alpha BC is equal to 1. And in case I ask you for AC, you can compare along J to get the value of AC. Okay. Any question on this? Okay. Now we will move to what we talked about at the beginning of the session. Okay. So when we have relative motion, we have several strategies. We can take a frame translating with the point, and this is of interest in general when we have 2 points on the same rigid body. And we have another approach which consists of taking a frame rotating with the body, and we will see that this will be interesting when you have a relative motion between a point and a rigid body. And we will understand better this when we give examples. So if you have, for example, a rigid body and you have an occupant on it, and this occupant can walk on the rigid body, this means that the occupant has a relative freedom with respect to the rigid body. So the vector AB will not have constant magnitude, it's changing in magnitude. Then B relative to A can do different types of motion, مش ضروري rotation. فيكون relative motion of B with respect to A rotation, بدأ يكون B fixed on the rigid body. ساعتها بنستعمل the previous approach. But in the case B can do any type of motion, okay? So what we will do then, we will take a frame fixed to the rigid body, يعني بيبرم مع rigid body, and B will have a possibility of moving relative to this frame لأنه هو قادر يمشي على rigid body. So whenever we have, if you want, a body that is able to have a freedom of motion relative to another body, and we want to get the relative velocity and relative acceleration, we will use the concept of rotating. Okay? And we will see how it will help us in getting relative velocities and acceleration in case we have general motion, and in case we have a rigid body in general motion that wants to measure relative velocity and acceleration of other points. So now we will develop the technique together, we will develop the formulas, and then we will apply problems on this. So to start with, what is the idea? The idea is to consider one point of the rigid body, let's say it's A, and we will put on A frame that is rotating with the body. يعني كيف بيروح البody بيروح معه الفريم. So imagine that you have for example, a rigid body doing general motion. You will put a frame fixed to the body. ساعتها the frame will have same angular velocity and acceleration of the rigid body. And in this frame, if you look at any point, you want to measure what is the velocity of this point relative to the frame. أعطيكم example. إذا بناخد B on the body ما عم يتحرك, بتكون ال relative motion تبع B with respect to the rotating frame 0. يعني A إذا عم يطلع على B بيشوفه fixed. Now in case B start to walk on the rigid body, then for example, if it's walking along a straight line, ساعتها relative velocity or relative acceleration بيكونوا, if B is walking towards A, يكون V relative و A relative of B with respect to A along this line مثلا. If it do a circle also it can, يعني it has a freedom. B في يعمل بده إياه على AB. And we will develop a technique to find the relative velocity of B measured by A, which is moving, which has a frame attached to it that is rotating with the ball. So what is the technique? First, since we are putting a frame at A, we will define the position of A with respect to the fixed frame. فعلى طول انتوا عندكم fixed و moving frame. With respect to the fixed frame, عندنا point A is characterized by position vector RA. Okay? While if you want to measure velocity and acceleration of B, the absolute, you need position vector RB. Now, as we did previously, to relate RA and RB to RB relative to A, the only thing we should do is to say that RA plus RB relative to A will give us RB. So this is the vectorial relation that will relate the position vectors. Now, what is little bit complex here هي الديريفيشن. لأنه when you want to derive قبل وقت أخذنا translating frame وعملنا derivative قلنا إنه B can only do rotation about A. ليه؟ لأنه كان distance between B and A fixed. كنا أخذين translating frame at A. So if we stand on the translating frame at A, we will see that B can only do rotation. فساعتها قلنا إنه VB relative to A هي omega vectorial AB. وقلنا إنه ال AB relative to A هي alpha vectorial AB minus omega square A. And that's it. Here, no, it's little bit different, little bit more complex. So to do the analysis, we will decompose each vector into its components. يعني vector AB is in which frame? I can consider that vector AB represents the relative position of B with respect to A in frame small x, small y. فإذا frame small x, small y, okay, represents this is the rotating frame. Okay, and big X, big Y هو الفixed frame. Now, so we will consider small I, small j for the rotating frame and big I, big J for the fixed frame. The vector RB relative to A can be written as XB times unit vector I plus YB times unit vector J. Okay. Now, the challenge is that when we want to derive this relation, if you remember, when we developed أنا وياكم the relation of relative velocity بchapter 12 قلت لكم إنه it's very important إنه يكون IJ translating frame. لأنه إذا كان IJ translating frame يعني IJ are fixed vectors ساعتها when I derive derivative تبعهم بتكون zero. Now it's completely different. And when I take a rotating frame, يعني I and J are changing in direction. So their derivative with respect to time will not be zero. يعني when you want to derive this term, when you want to derive RB relative to A vector with respect to time, you will have to derive U times V. يعني كأنه عندي UV يعني U prime V plus V prime U. So it will give you the following. It will give you dxB by dt along small I plus xB times di by dt. لأنه I is not a fixed vector. So صار بدنا نقدر نشوف بدنا نجرب نلاقي expression ل di by dt. What is di by dt? The same for deriving the second term. يعني derivative of ybj نفس الطريقة حتكون plus dyb by dt along j and plus yb times dj by dt. So the analysis with rotating frame is more complex because ij are not fixed vectors, they are moving vectors. So when I do the derivative, I should derive that. Okay? Now, we will do the analysis of each term. dxb by dti, okay, represent what? Represent Vx relative. It's the x component of the relative velocity in the rotating frame. So this is Vx relative I. And dyb by dt represent Vy relative. Okay? So this will give you these two terms, dxb by dti plus dyb by dtj, will give you really the relative velocity measured in the rotating frame. Okay? So this is Vy relative along j. So if you do the summation of these two vectors, Vx relative I plus Vy relative j, it will give you, so these two terms will give you V relative vector. So as you can see, the derivative of Rb relative with respect to ADT is equal to V relative plus something else. It's not just V relative, because you have other two terms, اللي هن xb di by dt and yb dj by dt. So now our purpose is to determine what is di by dt and what is dj by dt, to be able to find the expression. Okay? In order to find what is di by dt, we will do a small analysis تشبه اللي عملناه قبل بالUNUT. Same concept. You will see how. So let me draw it for you. If you consider vector ij at a certain position, this is ij. Okay? Now, your frame is rotating. فإذا باخد a very small time step, هيصير الفector I, let's say in this position, مثل الUNUT إذا بتتذكروا وقت عملنا الديمونستريشن، نفس الديمونستريشن. Same concept. So, what is vector di? This is vector di, and this is vector dj. So, this is di vector. And this is dj vector. So if you remember بالUNUT demonstration شو طلعنا؟ طلعنا انه DUT هي equal to theta dot UN إذا بتتذكروا. Okay. And DUN هي minus theta dot UT. عملنا demonstration together. So here, by analogy, okay, you can write that DI is equal to, as you can see in the figure, DI is parallel to J, and it's theta dot J. Okay, so sorry بس لحظة. DUT هي دي تتا UN. اوكي مش تتا دوت، لأنه بس نقسم على DT تصير تتا دوت. اوكي. So when you divide by dt بس تعملوا DUT over dt بتصير تتا دوت. خليني ارجع احط لكم اياها. يعني when you divide هي اصلا دي تتا، DUT هي دي تتا UN، ودي UN هي minus دي تتا UT. And when you divide by dt the two sides بصير عندكم انه DUT by dt هي تتا دوت UN. Okay. And here also the same. يعني you can write انه دي I هي دي تتا times J. وإذا نسيتوا كيف حأرجع أعملكم الديمونستريشن. Look. أول شيء دي I is perpendicular to I لأنه this is a very small angle. هيدا الانجل تقريبا 0. دي تتا is nearly equal to 0. صح؟ وعنا هول الفيكتورز unit vectors، يعني هيدا isosceles triangle. So if this angle is nearly zero and هيدا 90 degrees. So di is parallel to j. Okay, well, as you can see here هو same sense of j. So it's plus j times the magnitude. What is the magnitude of di? di هو small segment فحيكون equal the length of the arc of circle هيدا. And this arc of circle is the radius اللي هو 1 لأنه unit vector magnitude is 1 times d theta. Okay, so you can say then إنه di هو d theta j, and if you divide by dt, since you are interested in di by dt, di by dt is d theta by dt. شو هي d theta by dt؟ هي theta dot أو omega. Okay, so it's omega j. And in the same way you can demonstrate إنه dj هو opposite to I, it's minus. So since dj is minus d theta I, يعني dj by dt is minus omega I, is equal to minus omega I. So now if you replace back di by dt and dj by dt بالفورمولا اللي كتبناها أنا وياكم. Okay, so let us replace that. Okay, شو عملنا سوا؟ طلعنا إنه VB تحديت هلا is equal to VA, VB VA absolute plus V relative اللي هي summation of Vx relative along I plus Vy relative along J. So V relative vector. بقى عنا two terms if you remember. شو كانوا ال two terms؟ كانوا plus x small x times di by dt plus small y times dj by dt. Now I will replace di by dt and dj by dt by their values. Okay, قلنا انه فهيدا الترم حنجيبه انا وياكم is equal to what? This term. بقى عنا this term. Okay, عنا small x times what is di by dt؟ قلنا هي omega, so it's x omega times j. And what is dj by dt? هي minus omega I, so it's minus y times omega I. Now, if you look at this expression, okay, what is xy? xy هن ال coordinates تبع AB vector. لأنه look, in this figure, what is small x, small y? Small x, small y هن ال coordinates of point B in frame, in the rotating frame. Okay? يعني they represent the coordinates of B relative to A. So we can say that small xi plus small yj هو الفector AB. فإذا بتطلعوا بهالإكسبريشن بتذكركم بالresult of a vectorial product. لأنه if you do try to do omega vector vectorial AB شو بيطلع لكم؟ If you do omega vectorial AB, omega is along k, مظبوط؟ So if I replace omega k vectorial vector AB هو xi plus yj. Do this product, what do you get? هيدي الفورم هي بتشبه هي الفيكتوريال product formulation. لأنه from the vectorial product, if you do it here, you have k vectorial I plus j, يعني عندي equal to x omega times j and if I do k vectorial j بيطلع لي minus I, يعني minus y omega I. So try to compare, it's the same expression. Okay, so this term بالاequation تبعكم can be replaced by omega factorial AB. So as a final result شو حتكون in rotating frame شو حتكون general relation VB equals VA plus V relative plus هيدا term can be replaced by omega factorial AB. Let us compare with what we got before. وقتها كان عندنا 2 points on one rigid body. Okay? So now this is your relation, general relation. هتشوفوا انه هي بتطبق على rigid body of 2 points on a rigid body because مثل ما قلت لكم اذا برجع باخذ rigid body and 2 points fixed on the body وقت اخذ rotating frame at A واطلع ب B, B is fixed. Okay? فشو بيصير اذا B is fixed on the rigid body? VB relative to A will be 0. برجع لل previous relation that I developed with translating axis اللي هي VB equals VA plus omega factorial AB. بس هيدي الرول is very general لأنه بتزبط على 2 points fixed على rigid body وبتزبط كمان على points with relative motion. يعني إذا B بيقرر يمشي على rigid body ما بيقعد فينا استعمل previous formula تبع translating frame. مجبور استعمل ساعتها الفورمولا تبع rotating frame and I replace V relative by its value. Okay? So إذا بدكم هيدي it's a general rule that will work always. إذا كان الpoint fixed على rigid body برجع لل previous formula. In case it's not, I should add to VA plus omega factorial RB relative to A the relative velocity of B with respect to A. وإذا بدنا نعملها شوية interpretation فكروا فيه إذا أنا عندي body in motion plus أنا قادر أمشي على هالبودي فشو حتكون التوتال velocity تبع البوينت B؟ حتكون الفيلوسيتي اللي بيسموه هيدا coincident point. coincident point اللي هو البوينت اللي أنا واقف عليه هلأ بهاللحظة. الريجيد body حيعطيني الفيلوسيتي تبعه. هيدي هي الفيلوسيتي of the coincident point اللي هي البوينت اللي أنا واقف عليه. اوكي بلس لانه انا I have a freedom of motion اذا انا قادر امشي على البودي I should add to the velocity of this point I should add my relative velocity with respect to the body اللي هي V relative with respect to frame small x small y small z. okay in case وقفت يعني I'm not moving بصير كأني part of the rigid body ساعتها بتصير الفيلوسيتي تبعها هي الفيلوسيتي of the point of the rigid. Okay. If anything is not clear, I can repeat. Any question on this? Okay. The same procedure will be followed to get a general rule for the acceleration. بس لأنه it's little bit يعني long. الميثود هي ذاتها أنا كان بيهمني تفهموا من وين إجت relation. If you apply the same method for acceleration, you will end up with this formula. And I will just explain for you each term represent what. So for acceleration بعد it's more complex لأنه you have a lot of terms to derive. يعني هلا to get the acceleration relation you should derive the velocity relation. Okay? So if we derive the velocity relation and we apply the rules that we did together for V, we will obtain that for acceleration we have the following. The absolute acceleration of B اللي هي measured with respect عطول بس يحطوا بس AB أو AA يعني هيدي measured with respect to the big frame XYZ يعني absolute. So absolute acceleration of B is equal to absolute acceleration of A measured in big X big Y big C plus هيدا الترم هو alpha factorial AB اللي هنو ديجا نحن شايفينه قبل بالtranslating frame. Okay plus omega factorial AB هيدا الترم قلت لكم انه in 2D can be replaced by minus omega square AB يعني لحديت هلا nothing is new. okay هول التو terms هن ذاتهم تبع formulas of translating axis يعني اذا بدكم هيدي هول الترمز AA plus alpha factorial AB minus omega square AB هن الاكسلريشن of the coincident point يعني البوينت اللي نحن واقفين عليه على الريجيد بودي. اوكي. Now the effect of relative motion هلا حيبين بهول التو terms اللي هن 2 omega vectorial v relative. هيدي بيسموها Coriolis acceleration. Okay. And the Coriolis acceleration by definition is the acceleration due to the combination of rotation of the rigid body and the relative motion. يعني بس يكون عندي relative velocity مع الروتيشن حتعطيني شيء اسمه Coriolis acceleration. Coriolis acceleration. And finally plus a relative اللي هي represent the relative acceleration of the point with respect to the frame. Okay, so this is the general formula in case I have 2 points with 1 point moving on the rigid body أو outside of the rigid body كمان. هلا حناخد examples we'll understand better the application of these formulas. مثل ما لاحظتوا هول most general formulas لأنه in case عندي v relative و a relative 0 برجع بيطلع لي الفورمولا اللي كنت استعملها بال 2 points of a rigid body اللي هي AA plus alpha vectorial AB minus omega square AB. Okay, we will do a lot of practice on this. I know it's a little bit complex for you, but with the examples حتصير أهين الفكرة. Okay, any question on this? Okay, so let us do a small example so that you can understand better the application of this form. At the instant shown, theta is equal to 60 degrees. The rod has an angular velocity of 3 radians per second and an angular acceleration of 2 radians per second squared. At the same instant, the color C is traveling outward along the rod such that when x equals to 2 meters, the velocity is 2 meters per second and the acceleration is 3 meters per second squared, both measured relative to the rod. Determine the Coriolis acceleration and the velocity and acceleration of the color at this instant. هذا الexample بفرجيكم شو purpose of using this formula. يعني here what do I have? I have first a rod, a rigid body that has a motion of rotation and a rod that is rotating about the axis. طيب رجعت على الرod حطيت color and the color is not fixed on the rod. لو كان البوينت C fixed on the rod تلاقي الاكسلريشن و velocity of C تستعمل عادي relation between O and C is fixed relative to the rod. بس بما انه it's a color and it's able to slide on the rod يعني the color عنده relative motion with respect to the rod. And what is the type of this relative motion بهذا الexample? Translation. يعني الcolor is translating relative to a rotating frame. بمجرد ما يكون عندي body in motion relative to another rigid body فكروا تستعملوا general rule. Okay, so here they gave us the following. What do we know? First, we know omega of rod of the rod, omega rod R, omega rod is given والpha rod is given. So my rotating frame بعرف الأوميجا تبعه والألفا تبعه. الروtating frame حيكون fixed to the rod يعني بيبرم مع الرod. I take it in this way تقدر to decompose the motion of C into relative motion with respect to the rod plus the rotation effect of the rod. Okay? So the frame small x small y حيكون fixed to the rod حيبرم مع الرod. So this is x, this is small x, this is small y. Now, point C is doing what? Point C is translating on the rod. يعني relative motion تبعه is a rectilinear motion. So إذا بدي أكتب as I can see in the figure the relative velocity والrelative acceleration are along what? Are along the small x. إذا بدي أكتب الإكسبريشن تبعهم فيني أكتب إنه VC relative is equal to 2 small I. Okay. AC relative is equal to 3 small I. هلا please انتبهوا على شغله. I should always unify my vectors. يعني أو كل الفيكتورز بالvectorial relation بيكونوا function of small I small j. أو كل الفيكتورز بيكونوا function of big I big J. مهم لأنه آخر شيء بدي أجمع ال I component وال J component. So all I project all vectors على small I small j or I project all vectors على big I big J. أوكي؟ بنقل أهين لإلي. يعني أنا مثلا إذا بطلع بهالبروبلم أهين لي أشتغل بالإكسبريشن بسمول x small y. ليه؟ لأنه ال relative velocity are along small x. أحسن ما أجي أعمل projection. إذا بدي أشتغل ببيج x big y I can. بس ساعتها VC relative عندها 2 component بدي أعمل لها decomposition على big x يعني بعمل plus 2 cosine 60 big I و decomposition على big y اللي هي minus sine 60 big y. It is feasible. يعني any vector فيني أعمله function of small I small j أو big I big j. يعني مثلا VC relative أو بكتبها 2 small I أو بكتبها 2 times small I projecting it on big I big j هي cosine 60. Let me small I here equal to cosine 60 big I minus sine 60 big J. So I can easily move from one frame to the other. So أنا فيني أعمل expression أو function of small I small j أو function of big I big J. I choose the simplest form. For small j كمان فيني أعملها decomposition. As you can see here, small j on the positive x, positive y component, and this angle is 30 degrees. So I can replace small j by cosine 30 big I plus sine 30 big J. Okay. Now, since my terms are easier along small I small j أنا ضل اشتغل على small I small j. So I will apply the equations, okay, to velocity and acceleration relating point O and point C. Okay. So first, to start with the velocity relation, what do I have? I can write that velocity of C is equal to
دكتور
نعم.
في عنا صف تاني.
طيب okay, sorry يلا we continue next time. Okay, we continue this problem next time. Bye bye.
اوكي ميرسي باي باي.
Welcome. Bye.
Thank you, doctor.
Welcome.